Graph theory, example number 18. Use Dijkstra's algorithm to find the shortest path from A to G. So we have no context for this. We're just looking for the smallest number of units in the path from A to G. So recall that the first thing we do is we find the end point and we mark that as 0. Okay, the next thing we do is calculate the distance from the end point to the adjacent vertices. So it looks like we have a distance from G to E of 7 and a distance of from G to F of 6. Okay, now we look at those two vertices and we ask ourselves which one has the smallest value. And so that would be vertex F. We mark that as current and we mark vertex G as visited. Okay, so now I need to look at all the edges emanating from F that have not been visited. So I'm not going to look at this 6 right here because that leads us back to G, which has been visited. So 6 plus 2 to vertex E, well, that gives us 8. That's not any better than that 7, so we will not replace it. Okay, let's go to vertex D. 6 plus 4 is 10, and that came from vertex F. And then 6 plus 5 is 11. That came from vertex F. Okay, now we can mark vertex F as visited. All right, now I'm going to look at the totals that I have so far at the vertices. I have 7, 10, and 11. So that's going to make vertex E current. So I'm not going to look at the distance from E to G that's already been visited. I'm not going to look at the distance from E to F because F has already been visited. I'm only going to look at E to B and E to D. So 7 plus 6 is 13. I came from vertex E. And 7 plus 2 is 9. Now that is better than the 10 there. So I'm going to cross out the 10. And I'll put 9, and I came from vertex E. Okay, now that's all I can do from vertex E. I will now mark that as visited. Okay, so now I look at all my distances from my unvisited vertices, and I've got a 13, a 9, and an 11. So that makes vertex D current because it has that lowest total distance there. Okay, so I'm not going to go down this path anymore because E's been visited. I'm not going to go down this path anymore because F has been visited. So I only have 2 paths I'm going to go down. All right, so let's look at D to B. Is 9 plus 3, that's 12. Is that better than the 13? Yes. So I'll scratch out that 13 and I'll put it 12. Now where did I come from? Vertex D. And then 9 plus 2 is 11. That's not really any better, so I won't bother replacing that. Okay, so we're going to mark vertex D as visited. And so let's look at my total distances that I have at vertex B. I've got a 12. Vertex C, I have an 11. Okay, so that's going to make vertex C current. I'm going to go ahead and go back to black again. Okay, clearly I'm not going to look at D because I've already been there. I'm not going to look at the distance to F because I've already been there. I'm just going to calculate the distance from C to A. So 11 plus 4 is 15. Came from C. That's all I got, so I'll mark C as visited. So if I look at the 2 remaining vertices that have not been visited, that would be B and A. So B is a smaller distance. So I will mark that as current. So 12 plus 1 is definitely better than the 15. So I have 13, and I went from, that is from vertex B. So my optimum distance is going to be 13, but they asked me for the shortest path from A to G. So I will find that. So I begin at A. Where did I come from? B. Let's go to B. Where did I come from? D. Right, let's go to D. Where did I come from there? E. Okay, let's go to E. All right, and then we, of course, end up at G. So again, I think you see why I leave those little breadcrumb trails. So I have visited many sites to try to figure out the best method. And what I've shown you here is a combination of a couple methods that I've seen that seems to work out best.